Hello everyone, this is Mr. Kaviani, and by the end of this series of videos, you should be able to calculate the rotational kinetic energy of objects, determine the work done by a torque, and use rotational kinetic energy and conservation of energy to analyze the energy of a system. Alright, so when it comes to rotational motion, we haven't yet discussed the concept of energy. Now, we know earlier when we learned about linear or translational motion that the motion of an object was associated with a type of energy known as kinetic energy. And we defined the linear or translational kinetic energy of an object to be 1/2 times the mass of that object times its speed squared. But what about objects that are rotating, right? They're moving too, aren't they? So it would make sense that objects that rotate also have some form of kinetic energy, but objects that are going like purely rotational motion, for example, like this wind turbine right here, doesn't really make a whole lot of sense to talk about translational kinetic energy for an object undergoing mostly rotational motion. And so we have to define a new term of rotational kinetic energy. And we'll skip the derivation for now, but the formula for rotational kinetic energy looks very, very similar to translational kinetic energy. It's going to be 1/2 times, and not the mass, but as you've seen before with Newton's second law, we've replaced mass in rotational motion with I, moment of inertia, the distribution of mass of an object. And we'll multiply not by v, our linear velocity, but by omega, our angular velocity squared. And so in this way, the formula is almost identical to the formula for translational kinetic energy. Now, while these videos on the screen represent discrete forms of just linear and just rotational motion, it's very possible to have a combination of translational and rotational kinetic energy. For example, like a bicyclist riding a bike. Their bike and their body are moving linearly through space and have translational kinetic energy, but their wheels are rotating and therefore also have rotational kinetic energy. And so you can have a combination of these energies as well. All right. We can also define a rotational form of work. And remember, work was just a change in energy. And so if we said earlier that in order to change the amount of energy an object had, we had to exert a force on that object. And then we multiplied the force by the displacement of that object. We used d for displacement, but you'll remember that d also is just delta x, right? This is just talking about the idea of displacement. And so we'll go ahead and use delta x here for a specific reason. But we said the work on an object was the parallel component of force. So this symbol means the parallel, right? Parallel to displacement. Sometimes we would use an FD cosine theta, right? This cosine theta term helped us get that parallel component, or the amount of force in the direction of the displacement, not the parts that were not pointing in the direction of displacement. That was how we changed the energy of an object. And so if something's not moving and you push on it and you push on it for maybe 3 meters, right, you are doing work on that object, you are giving it, let's say, kinetic energy. And so work was a change in energy. It was equal to a force multiplied by a displacement. And so in the very same way, for rotational motion, right, in order to change the amount of rotational kinetic energy an object has, we need to apply not a force, but a torque to it over a certain displacement. And so on the right, for example, you have a wheel, and someone's spinning a wheel with their hand. So they're pulling on the wheel, they're moving their hand on the edge of the wheel, trying to get it to start spinning. So they're applying a torque to the wheel, and we know that their torque is just going to be the r, the radius away from the edge, right, from the center to the edge, multiplied by F. And in this case, this force is completely perpendicular to the lever arm, so I'm not going to include any sort of sine theta term. So the torque here would just be Rf. If they apply this torque for a certain angular displacement, maybe they do that for 2 rotations, right? We can figure out the total amount of energy, rotational energy, that they gave the wheel. And so just like force and displacement in linear terms, we will use instead for work in rotational terms, torque multiplied by not linear displacement, but my angular displacement, delta theta. Now, in this case, we don't need to worry about a parallel component of torque because when we look for torque, when we calculate torque, we're already considering the amount of force that is, in this case, perpendicular to the lever arm or in the direction of the wheel's displacement. So that's accounted for already. So we can use this expression to help us find the change in rotational kinetic energy of an object if we know how much force we're applying to something and the distance away from the center that we're applying it for. All right, and so because we're discussing energy once again, we're going to revisit our energy bar charts and LOL diagrams to help us model the energy change of a system. In this case, I've modified our energy bar chart diagram to also include this kinetic energy rotational term. And so now we have a way of keeping track of our translational kinetic energy. So this is for linear motion. And we have a way to keep track of our rotational kinetic energy separately. They're going to be two separate forms of energy, both before in our initial state and after in our final state. And once again, in the system, we list the objects that are part of our system and any works being done. So if there's going to be any positive work, so any positive work would be coming into the system, and then any negative work or a reduction in the system's energy would be leaving the system or flowing out of the system. And so we can use this diagram to help us model the energy change for complex scenarios. If we do, we will get our energy conservation equation simply by evaluating the terms that we have and eliminating the ones that we do not from our energy bar charts. So this really simplifies the problem-solving process and acts as a very helpful guide when solving problems, especially when there are multiple forms of energy present. And lastly, if you've forgotten, our U sub g represents gravitational potential energy, or the energy an object has due to its position above the Earth, stored in that gravitational field between the Earth and that object.